Hello, everybody. Mr. C here. Just wanted to give you another resource. This is from your ABU substitution with algebraic techniques notes. We'll be doing examples 5 and 6. So that's a total of 6 problems. Let's jump into it. So this is 5a. 5a asks us to find the integral of x to the 5th minus 35x divided by x squared plus 6 dx. So you might try U-substitution, but you'll quickly find out that if I pick the bottom to be u, we'll get a derivative du as 2x. That looks nothing like this x to the 5th term up here. Similarly, if we choose the top to be u, and we take its derivative to get our du, we do not get an x squared term, we get an x to the 4th term. So we can't immediately use U-substitution. What do we do? What you want to do for these kinds of polynomial problems when you have a division is actually do the division. So this will be a quick review of polynomial long division. You write the top, and it's helpful to write the blank terms in between. So we go straight from x to the 5th to x to the 1st here. I'm going to instead write a bunch of 0 terms. Sometimes this isn't super helpful, other times it's very helpful. So I just make a habit of doing it always. Okay, so now we have 5, 4, 3, 2, and then 1. That's good. And then same thing for the denominator. It's helpful to write the 0 terms. So we have 0x here. Now, when we're doing polynomial long division, it's key to look at the first term. Okay, so we're going to look at the first term, and we're going to ask, is there anything I can do? Can I multiply anything to this first term in order to get this first term? And the answer is yes. If we multiply x squared by x cubed, we add the powers and get x to the 5th. So we're going to say, yeah, x cubed. And then we multiply x cubed by each of these. So x cubed times x to the 2nd gives us x to the 5th. Plus x cubed times 0x gives us 0x to the 4th. Plus x cubed times 6 gives us 6x to the 3rd. But if you remember from regular long division, we don't add these terms, we subtract all of them. So we basically end up flipping the signs of all those terms. And when we do that, we see that our x to the 5th terms cancel out, right? That was the point. That's why we said, hey, what can I do to get x squared to be x to the 5th? That's why we put x cubed in the first place. So this is 0, this is 0, and then we have negative 6x cubed here. And then we're going to bring down the rest of our terms here, or the next term. Doesn't really matter. So I'm just going to write the rest of them. And we're going to ask the same question. What can I multiply to x squared to get negative 6x cubed? The answer is, well, we need a negative 6, right? We need to multiply by negative 6 to get the coefficient, right? And then we need another x. So it's going to be negative 6x. I just like to line these up based on their powers. You don't really need to do that. It might be helpful. Same deal as before. We have our new term. We're going to multiply our new term by each of these. So we have negative 6x times x squared gives us negative 6x cubed. Negative 6x times 0x gives us 0x squared. And then negative 6x times 6 gives us negative 36x. And again, we don't want to add these. We want to subtract them. So we're going to flip all the signs. When we do that, we see These cancel out, these stay 0, and negative 35x plus 36x gives us a lonely x. All right, at this point, let's try it again. Let's say, what can I multiply to x squared to get x? Well, there's not much we can do. We could multiply by maybe thinking about multiplying by a fraction, but that's not how we do division. So when you get to a point where the power of your remainder here is less than the power of the first term here, the leading term, then you just write the remainder as remainder over divisor here. So this is the way for writing your remainder with polynomial long division. We get to a point where our power of our remainder is less than our power of our greatest term in our divisor. So we just write remainder divided by divisor. Okay, why did we do that? Well, we can now rewrite this complicated expression, right, as the integral of x cubed minus 6x plus x over x squared plus 6. And of course, we need our dx. So I'm going to just move this down. What do we do from here? Well, I would suggest that you break this integral up, right? This stuff's just going to be power rule. This looks a little more complicated. So let's break it right here. This is one of the properties of integration. It's called linearity if you're interested. But basically, we can just rewrite the integral as multiple integrals if they're added or subtracted. So I wrote the first term, don't forget the dx, and then another integral of just the second term. Why would we want two integrals when we had one before? Well, it's actually easier to work in smaller bits like this sometimes. So first of all, let's just figure out what's going on in the second integral. Notice if we look at this denominator, we have an x squared term, and if we were to take its derivative, we'd get an x to the first term. So that suggests that we would want to make u x squared plus 6. We find our du. Derivative of x squared plus 6 is 2x dx. And then we can solve for dx by dividing both sides of our du equation by 2x. We get dx is du over 2x. So let's plug in our u, plug in our dx. Nothing new here. Don't forget this term right here. We have not dealt with that yet. So we need to rewrite it. But now we said u was x squared plus 6. So I'm going to write u in the denominator. And then dx was du over 2x. So I'm going to change dx to du over 2x. And I still have the x in the numerator. Okay. At this point, again, we have this same term. We didn't do anything with it yet. And we can see that the x's can cancel out. We do have this 2 in the denominator. But because that's just a constant multiple, we can pull it out of the integral as a 1/2 because it's in the denominator. And rewrite this as du over u. Okay. We can do our check. We just use U-substitution. Do we have any x's left in this integral? No, we do not. That means we're on the right track. That means let's find some antiderivatives. Now let's figure out this bit here. This is just power rule, or two instances of power rule for integrals. We increase the power by 1 and divide by that power. Same thing here. We increase the power by 1 and divide by that power. Now moving on to this part, we have plus a half. Integral of du over u is the natural log of the absolute value of u. And of course, this is an indefinite integral or two indefinite integrals. We need plus c. All right, so we can substitute our u back in. So now we have 1/2 natural log of the absolute value of u was x squared plus 6. And we can do a little simplification here. 6 divided by 2 is 3. And we could leave it here. However, whenever you have absolute value bars, they might not always be necessary. So in this case, we can look at the part inside the absolute values and say, wait a second, no matter what number I put in for x, right, it's going to be squared. So if I put in a positive number, I'll square it and get a positive number. If I put in 0, I'll square it and get a positive number, or sorry, 0. And if I put a negative number, most importantly, I'll square it and get a positive number. So no matter what I put in for x, this is going to be positive, meaning these absolute value bars are actually redundant. We do not need them. We can write them with parentheses instead. Now I want to make it really clear, that is not always going to happen. It only happens when whatever you could possibly put in for x, any real number, in for x, you would always get a positive number. And that is the answer to 5a. Let's move on to 5b. 5b now is asking us for the integral of dx over x squared minus 4x plus 4. Now again, we can look and say, maybe we want to use U-substitution. And it turns out that, well, the only real term we see here, we have 1 times dx on top. That's not much to work with. We have x squared minus 4x plus 4 on bottom, right? But when we make that our u, then we'll take the derivative to get du and get a 2x minus 4, right? So if we were to say this, u is the whole denominator and we find du, we have a problem. This is not present anywhere in this problem at all. So this kind of means there's not much we can do with U-substitution, at least yet. So is there a way we could rewrite x squared minus 4x plus 4? Yes, there is. Of course there is. So x squared minus 4x plus 4, it's actually equal to x minus 2 times x minus 2, right? The way that I found this, right, 2 times 2 or negative 2 times negative 2 gives me 4. And then basically what I'm getting at is foiling here. If we FOIL this back, we get x squared minus 2x, oops, wrong one, minus 2x again, minus 2 times minus 2 is plus 4. So we can simplify this. This part becomes negative 4x. Okay, so we could write it like this, or perhaps better, we could rewrite this as, this is just something times itself, so we could rewrite it as that thing squared. So now our integral is dx over x minus 2 squared. The question is, can we now use U-substitution? Well, maybe first we can rewrite this as a positive, sorry, not a positive. We can rewrite this exponent in our numerator by making the exponent itself negative. And if we were to make u equal to x minus 2, then du is just dx. So our new problem becomes, instead of x minus 2, we have u to the power of negative 2. And instead of dx, we have du. Did we do anything wrong? Is there any x's? No, just u's. That means we did it right. We're good to go. Let's take an antiderivative. Again, this is just power rule. We increase the power by 1 and divide by that power. And then we have our plus c, of course. Finally, let's plug back in for u. We get x minus 2 to the negative 1 divided by negative 1 plus c. You can leave it like this, or you can rewrite it a little bit. We can move this to the denominator. So we have 1 over x minus 2 to the 1. So I don't need to write those parentheses. But we have this negative 2, not negative 2. We have this negative also. So we want to make the numerator negative. There are a few different ways to write this nicely. Again, you can just leave it like this, totally fine. Right, moving on, 5c. So 5c looks, well, we'll see. It looks like we can use U-substitution. So let's try it, right? We've seen something like this before where we had a fraction, it had some e to the x's, one of the terms was added to something. So as we saw last time, we made the numerator in this case our u, because we know that we're going to take the derivative and this constant's going to disappear. So when we do that, derivative of e to the x is itself e to the x, derivative of a constant is 0, and we have our dx. So if we solve dx, the du equation for dx, then we can divide both sides by e to the x, and we get dx is du over e to the x. So let's plug in dx and u, just as we normally do, and find out what happens. So u was that top bit there, that's u. We haven't changed the e to the x yet. And dx is du over e to the x. Okay, we normally would expect to see a cancellation here, but is this what happens? Notice, if I multiply, this is the same as writing this. Just multiplying the numerators and dividing by the product of the denominators. So we could rewrite this as u du over e to the 2x. Wait a second. We didn't get a cancellation, right? Instead, we basically squared a term. We squared a term. We have x's is the bottom line. We did our u substitution. We wanted to get rid of all our x's, and we did not get rid of all our x's. So this is why I always say you should probably do a check here, see if there's any x's where you would expect just to have u's. In sum, this is not the right way to do the problem. Instead, let's try something else. For your reference later, let me just make this super clear. Okay. All right, so there's got to be another way to do this. Maybe. We'll see. This is just a little algebraic trick. If I have some stuff divided by a single term, I can actually split this division. And what I mean by that is instead of dividing both of these by e to the x at the same time, I can divide them individually by e to the x, right? And I keep the sign between them. I divide this term by e to the x as well. Okay, so again, all I did here was split this fraction. We can do that because the denominator is just a single term. If you had something like this, this would not, well, we'd need to, split it each like this, but we don't have that. Okay. All right, what happens here? Well, something pretty nice, right? E to the x divided by e to the x is 1 plus 4 divided by e to the x. All right, we can't do much with that. Maybe we could put this in the numerator. We can do that by negating the exponent. Okay, and again, here I'm going to suggest that we separate this integral into two separate integrals. So instead of the integral of 1 plus 4 times e to the x dx, let's write this as the integral of 1 dx plus the integral of 4 e to the negative x dx. Again, this is what we did in the first example, just separating the integral. Okay. We can actually, well, actually, we'll do that in a second. Let's look at this term here. I don't know what the integral of, or the antiderivative of e to the negative x is. So let's make u equal to negative x. So when we take du, we get negative dx, which means that dx is negative du, right? Just multiply -1 to both sides. All right, and now only for this part, let's plug in our u and our dx. Only for this part. Let's keep this one the same. So we still have 1 dx, integral 1 dx over here. And now we have 4e to the u. And instead of du, we have, instead of dx, we have a negative du. Okay, do I have any x's here? No, I don't. That means U-substitution was okay. Just going to rewrite this term. Now, we have some constants here. We have a 4 and we have a -1. So we can pull out the 4 and the -1. So that's -4 times the integral of e to the u du. Okay, let's take some antiderivatives. The antiderivative of 1 is x. We have our -4. The antiderivative of e to the u, well, that's e to the u. And of course, we have our plus c because these are indefinite integrals. Okay, at this point, all we have to do is plug back in for u. And we said that u, whoops, there it is, u is negative x. We only have x's, we are good. All right, last one for 5 before we get to 6. So 5d is the integral of x cubed minus 7 squared dx. I don't see any immediate antiderivatives for this, right? This is a little too complicated. I mean, if the square and the parentheses weren't there, right? If this wasn't here and this wasn't here, then we could just use power rule. But this is a little more complicated. I also don't see how we could use U-substitution. Again, typically we look in our parentheses. I'm going to say this every single time, but I need to say it again. This is not a hard and fast rule, but it is just a suggestion. It is something to start with. Look in your parentheses. Try to make something that you have in parentheses equal to u. And then we take the derivative. Derivative of x cubed is 3x squared. Derivative of -7 is 0, right? We don't have any 3x squareds here, right? that's a problem. So is there something else we could try? Yes. Well, from our algebra class, we know that if we have a polynomial squared, that's just the same as writing the polynomial times itself. Okay, and from here, we can multiply. So you can use your little box diagram if you want, or you can use your foiling method. For foiling, we do our first term times our first term here. X cubed times x cubed is x to the 6. First outer, we do our outer terms. X cubed times -7 is -7x cubed. Inner, we do our inner terms. -7 times x cubed is again -7x cubed. And then our last terms. -7 times -7 is +49. And again, we can rewrite this by combining like terms. -7x cubed minus 7x cubed is -14x cubed. All right. So we can rewrite our integral as, instead of this, just a bunch of powers. By now we're pros, we know how to use power rule for each of these terms. So let's do it. We don't even need U-substitution for this one. Right? Using power rule, we increase the power and divide by that power. Minus 14x, increase the power, divide by that power. And then plus 49, increase the power. Well, okay, that means we get x. Divide by the power of 1 is 1 on bottom. And we have plus c, because this is an indefinite integral. This is pretty much done. We can't really do much more. We can simplify this term a little bit as 7/2 instead of 14/4. Doesn't matter too much. But other than that, this is our final solution. Okay, on to 6a. Now, I want to make a note. The answer that was provided, if you're looking at your note sheet, there is a completed note sheet as well. I don't know if you typically look at that or have access to that, but it does exist. If you're looking at it, there is a slight mistake in one of the constants of our answer. So I'll make a note when that happens, but it's the same process. So if you're following along and you don't realize it, that's okay. But I have made the correction in my notes. So anyway, let's do it. We got the integral of x plus 1 times the square root of 2 minus x dx. You all know me, you know what I'm going to say. I don't like square root signs. Let's rewrite this as the integral of x plus 1 times all that stuff under the root to the 1/2 power dx. Okay. So let's try U-substitution. Typically, we look at the more complicated expression, right? So maybe we make u the inside part here. Let's say u is 2 minus x. Then we get du to be, well, the derivative of 2 minus x is -1 times dx, which means dx is negative du. And let's plug in u and our dx. So when we do that, we get, well, we haven't done anything with this term here. And we have a u. Instead of 2 minus x, we have u to the 1/2. Instead of dx, we have negative du. All right, time to break the golden rule that I've been saying the whole time. We do our check, right? We didn't cancel out all our x's, but this is a linear term, right? It has a power of 1. And notice for our u's, we had a linear term as well, x to the power of 1. So what if, instead of giving up here and trying a new solution, what if we instead solved this for x? So we can do that by adding x to both sides. We get u plus x equals 2. And then we subtract u from both sides. We get x equals 2 minus u. So instead of abandoning it here, let's also plug in our x, because our x is in terms of u, right? We're trying to get all u's. So let's plug in when we can. So this comes out to be, instead of x plus 1 here, we have 2 minus u plus 1 times u to the half times a negative du. Okay, now have we gotten rid of all our x's? Yes, we have. We just have u's, that means we're good to go. And in this next step is where the mistake happened in the notes. It's just a small mistake. The author did 2 minus 1 instead of 2 plus 1, and that threw off the final answer by a constant. Not a huge deal. But let's simplify some stuff. I have this negative du, right? That's just a negative 1. I can pull out the negative 1. I have 2 plus 1 is 3 minus u times u to the half du. Okay. Now, this is still a little complicated. So how about we distribute this u to the half to both of these terms? Why would we do that? Well, then this 3 times u to the half becomes 3u to the half. And then negative u times u to the half gives us negative u to the 3 halves du. So why do we do that? Because now we just have an instance or 2 instances of power rule. And we like power rule. It's easier than the other stuff. Okay, so let's find some antiderivatives. We have a negative out front, so we can't forget that. Again, power rule, we write what we had, but we increase the power by 1. We make that a little more legible. And then we divide by the power that we have now. Same deal here. We increase our power by 1 and divide by our power that we just wrote. Right, increasing a half by 1 gives us 3 halves. Increasing 3 halves by 1, that's the same as increasing by 2 halves. So that's 5 halves. Okay, we can do a little bit of simplifying, right? If I have 3 divided by 3 halves, that's the same as 3 over 1 times the reciprocal of the denominator. And then over here, if I have 1 divided by 5 halves, that's the same as 1 times the reciprocal of the denominator. Okay. And there's one more little thing we can do, right? I have a negative here. So if I distribute the negative sign, then this term becomes negative and this term becomes positive. Now we can do some simplifications. So we have 3's cancel out. We have 2 over 1 or negative 2 over 1. That's just negative 2u negative 2u to the 3 halves plus 2/5 u to the 5 halves plus c. And finally, we need to plug back in for u. So what was our u? It's been a while. U was 2 minus x. And we plug it in again, 2 minus x. And we have our final answer. Okay, this term was a little bit incorrect because of the in the notes, like I mentioned earlier. Just this part, the negative 2 was something like, I think it was negative 2/3 or something in the notes. So it should be negative 2. All right, last one, 6b. We have the integral, no surprise there, of 2x plus 1 divided by square root of x plus 4 dx. All right, again, I don't see any immediate antiderivatives, right? I feel like we're going to use U-substitution. I'm not quite sure, but I do see one term that's more complicated than the other, right? Square root term, a little more complicated than just something without a square root. So before we, try U-substitution or whatever, let's rewrite this as I always do. So we keep that numerator, and then we can multiply by, well, square root means the half power. And then we move it to the numerator from the denominator, so we need to negate the power. So we are multiplying by x plus 4 to the negative 1/2. From here, clearly this is more complicated, right? We're raising all this stuff to the negative half. Here we're not raising any power. So let's say maybe u is x plus 4. Give it a try, see what happens. We find du. So du would be, we take the derivative of x plus 4 with respect to x, then we get derivative of x is 1, plus derivative of 4 is 0, so we have 1 times dx, or just dx. Okay, let's do exactly what we did before and what we've been doing. Let's plug in for u and for dx. So we haven't touched this term yet, right? Instead of x plus 4, we have u. We're raising it to the negative 1/2. And instead of dx, we have du. Let's do our check. Do we have any x's? Yes, we do. Unfortunately, we do. Does this mean we have to abandon it and start all over? Well, if you remember from the last example, we kind of could work around it, right? So maybe instead of abandoning this, and our goal is to write this all in terms of u, let's solve this u expression or equation for x. So if we subtract both sides by 4 for our u equation, we get x is u minus 4. And let's now plug that in for x right here. So our integral is, instead, we have 2 times u minus 4 plus 1 u to the negative half du. We distribute this 2. We get 2u minus 8 plus 1. Well, minus 8 plus 1 is minus 7. U to the negative 1/2 du. And then the same thing as the last problem, right? Why deal with a product when we could distribute this term here to both of these and just have to deal with power rule? So 2 times u to the negative half. Well, this is just u to the 1. So we add these two exponents, we get 1 minus a half. 2u to the positive half now, right? We just add the exponents. Negative 7 times u to the negative half is negative 7u to the negative half. And we have du. All right, we reduce this just to power rule for integrals. So this is equal to 2 times u, we increase the power by 1, that's 3/2, and we divide by 3/2. Minus 7u, we increase the power by 1, that's 1/2, divide by the power, 1/2, and we have plus c. Same thing as before, we can rewrite this as 2/1 from the numerator times the reciprocal of the denominator, which is then 2/3 times u to the 3/2, minus, same thing. We have a 7 in the numerator, that's the same as 7/1, times the reciprocal of our denominator, that's 2/1, u to the 1/2, plus c. And finally, we can simplify a little bit. We got 4/3 u to the 3/2 minus 14 over 1, or just 14, u to the 1/2 plus c. And our last step is to substitute back in for u. U was x plus 4. So we have 4/3 x plus 4 to the 3/2 minus 14 x plus 4 to the 1/2 plus c. And if you wanted, you could rewrite this the square root, but I don't feel like writing that all over again. Okay, I hope this was helpful. Please let me know how else I can support you. Y'all are doing great. I appreciate you. And I will see you in class. Thanks.